Hey everyone. I always get that line from our theme song stuck in my head.
Oh,
It's
yeah.
that one about Professor Wu.
Oh, right.
Professor Wu's got the secrets.
It is super catchy, yeah.
If you haven't heard it yet, definitely check it out.
Yeah, it's a good one.
But speaking of secrets today, we're doing a deep dive on conditional entropy and information gain.
Oh, those are good ones.
Yeah,
Those are really interesting concepts.
yeah, and they're pretty powerful too when you start to think about how they're used.
Yeah, especially for like building decision-making models and stuff.
Exactly. And I think a lot of folks find the idea of entropy a little intimidating.
Yeah, it does sound a
You
little
know,
scary.
It's like, oh no, am I going to have to remember my physics textbook for this one?
Right, right.
Can you help break down what exactly we mean when we say entropy?
Yeah, so you can think of it like as a measure of chaos or uncertainty in a system.
Okay.
So like imagine you have a jar full of marbles
Okay.
and they're all different colors and they're totally mixed up.
All right, I'm picturing it.
That's a really high entropy situation because there's a lot of randomness, right?
Okay.
You can't really predict what color you're going to get if you just pull one out.
Yeah, that makes sense. So a more chaotic system like our jumbled marbles has more entropy because there's just more uncertainty.
Exactly. Yeah. And then imagine that we start to organize those marbles, like we separate them out by color.
Yep.
Suddenly the system becomes way more predictable.
Right.
We've gained information about the jar and how it's arranged. And as a result, the entropy decreases.
So gaining knowledge always reduces uncertainty and therefore reduces entropy.
Yeah, exactly.
Okay, that makes sense. But I'm thinking like we don't always deal with these perfectly arranged marble jars in the real world.
Right.
So how does conditional entropy come into play here?
Yeah, so conditional entropy is all about understanding how much uncertainty is left over after we learn something new.
Okay.
So let's say we peek into our marble jar and we see a single red marble. So in this case, the conditional entropy represents the remaining uncertainty about the other marbles in the jar, given that we know there's at least one red one in there.
So it's like, okay, we know something now, but how much is still a mystery?
Exactly.
And I'm guessing this leftover uncertainty is always less than or equal to the original entropy because we've gained at least some knowledge.
Exactly. Yeah, you got it.
Okay, I'm with you so far. And this brings us to information gain, right?
Yeah,
Which is basically the difference between our initial uncertainty or entropy
right.
and then the remaining uncertainty or conditional entropy after we've learned that new piece of information.
Exactly.
So a larger information gain means we've learned something really valuable, something that significantly reduces our uncertainty.
Yeah, it's like that aha moment.
Yeah, like a piece of the puzzle has fallen into place.
Exactly. And here's why this is so powerful.
Okay.
By calculating information gain for different pieces of knowledge, we can figure out which ones are the most helpful for reducing uncertainty and making better decisions.
That's super interesting.
But let's not get ahead of ourselves.
Right.
To really grasp this, we need a concrete example.
I was just thinking about that example from Professor Wu's lecture where he was talking about predicting if someone played golf based on the weather.
Oh, yeah.
Something about how knowing the outlook was more informative than knowing the temperature.
Yeah, that's a perfect example.
Maybe we can
Yeah.
use that to kind of illustrate how all of this actually works.
Okay, yeah, let's dive into that.
All right, so let's break down this golf example.
Okay.
I remember Professor Wu's data showed that knowing the outlook, like was it sunny, overcast, or rainy, gave us more information gain than knowing the temperature.
Right.
How did he actually figure that out using conditional entropy?
Okay, so let's go step by step.
Okay.
Our starting point is the entropy of playing golf.
Okay.
So this represents how much uncertainty we have about whether someone played golf without knowing anything about the weather.
Okay.
And in his data, this initial entropy was around 0.94.
Right. So that 0.94 basically tells us it's pretty much a toss-up whether someone played golf or not.
Exactly.
We need more information.
We need more information. Yeah.
Okay.
So now to calculate the information gain for outlook, we need to determine the conditional entropy of playing golf given the outlook.
Okay.
So this means we got to look at each possible outlook, sunny, overcast, rainy,
Okay.
and see how it influences the likelihood of playing golf.
So for each outlook, we're kind of creating a mini picture of how often people played golf in those specific conditions.
Exactly.
Got it.
And then we combine these many pictures, taking into account how often each outlook occurs to get the conditional entropy of playing golf given the outlook.
Okay.
And in this case, that calculation gives us a value of about 0.693.
Hold on. How did we get that 0.693 number?
Oh, yeah. Good question.
Is it just based on how many times people played golf when it was sunny versus overcast versus rainy?
It's a little more nuanced than that.
Okay.
We're not simply looking at the overall distribution of playing golf. For each outlook, sunny, overcast, rainy, we calculate a kind of mini entropy based on how often people played golf in those conditions.
Gotcha.
And then we combine these mini entropies, giving more weight to the outlooks that occur more frequently.
Okay.
And that weighted average gives us that 0.693 value.
So it's like we're saying, okay, sunny days happen this often.
Yeah.
And on sunny days, people play golf this much. Overcast days happen this often. And
Right.
okay, I see how it comes together.
Yeah.
But how do we then use that 0.693 to actually get the information gain for Outlook?
It's surprisingly simple.
Okay.
We take the initial entropy of playing golf, that 0.94,
Oh,
and we subtract the conditional entropy given the outlook, the 0.693.
okay.
And the result is 0.247.
Okay.
That's the information gain from knowing the outlook.
So knowing if it was sunny, overcast, or rainy
Mm-hmm.
reduced our initial uncertainty about playing golf by 0.247,
Exactly.
which is pretty significant.
Yeah.
And I assume if we repeat those calculations for temperature, we would get a smaller information gain.
Exactly. And that's what Professor Wu found in his analysis.
Okay.
Knowing the outlook gives us more bang for our buck, so to speak, than knowing the temperature when it comes to predicting whether someone played golf.
This is making so much more sense now.
Good.
And I'm guessing this is why Outlook would be chosen as a key factor in like a decision tree or something.
Exactly.
It gives us the most valuable information right off the bat.
You got it.
Awesome.
And you know, the beauty of information gain is that it's not just about decision trees.
Right.
It's a fundamental concept that helps us understand which pieces of information are truly valuable for reducing uncertainty, regardless of the specific application.
That's really cool.
Yeah.
I have to admit, my brain is starting to feel a little overloaded, though.
Oh, yeah. I can imagine.
Maybe we could take a little break here,
Yeah, let's do that.
and then we can dive into the actual calculations and formulas in the next part.
Sounds good. Let's give everyone a moment to absorb all this amazing information.
Yeah. All right, I think I've caught my breath. We covered a lot of ground with conditional entropy and information gain,
Yeah.
but I'm ready to tackle the math now.
Okay.
Are there formulas involved?
There are.
All right. I'm a little nervous, but also kind of excited to see how it all works under the hood.
Yeah.
So let's start with the entropy formula. What does that look like?
Okay, so we use the letter H to represent entropy,
Oh,
and the formula looks like this.
okay. I see a summation symbol, which means we're adding a bunch of things together.
Yeah.
But what are those things exactly?
Yeah, so each term in that summation represents the contribution of a specific outcome to the overall entropy.
Okay.
So imagine we have a variable with three possible outcomes, A, B, and C,
Right.
and each outcome has a probability of occurring denoted as PA, PB, and PC.
Right. So those probabilities just tell us how likely each outcome is.
Exactly.
Like if outcome A has a probability of 0.5, that means it's expected to occur half the time.
Exactly.
Okay. Yeah.
Now, for each outcome, we calculate a term in the entropy formula. It's the probability of that outcome multiplied by the logarithm base 2 of 1 divided by that probability.
Okay. I'm seeing it now. So for outcome A, the term would be PA times log base 2 of 1 over PA.
Exactly.
But what's the intuition behind that calculation?
Yeah, good question.
It seems a bit mysterious.
Yeah, so that logarithm term is actually capturing the surprise or information content of each outcome.
Okay.
The less likely an outcome is, the more surprised we are when it occurs and the more information it conveys.
That makes sense.
Yeah.
So if we flip a coin and get heads, it's not very surprising because it's a 50-50 chance.
Yeah, right.
But if we roll a die and get a 6, it's more surprising because there are 6 possible outcomes.
Exactly. And the logarithm function captures this intuition mathematically.
Okay.
So the less likely an outcome is meaning the smaller its probability, the larger the value of log base 2 of 1 over p will be.
So when we add up all those surprise terms for each outcome,
Right.
we get the overall entropy, and that represents the total uncertainty of that variable.
Right.
Gotcha. Now, what about conditional entropy? How does the formula change when we add that given condition?
Yeah, so the formula for conditional entropy, written as h of y given x, builds upon the entropy formula we just discussed.
Okay.
It's essentially the same idea, but now we calculate the entropy of y for each possible value of x,
Okay.
and then we average those entropies weighted by the probability of each x value occurring.
So we're breaking down the entropy of y into smaller chunks based on the different values of x, and then we combine those chunks to get the overall conditional entropy.
Yeah, exactly.
Okay, and that makes sense intuitively, right?
Yeah.
If knowing x tells us something about y, then the uncertainty of y should decrease when we factor in x.
Right, exactly like that red marble example again.
Right.
Knowing the color of one marble gives us some clues about the other marbles, reducing our overall uncertainty.
Exactly.
And then to wrap it all up, to calculate information gain, we simply subtract the conditional entropy from the original entropy.
Okay.
The bigger the difference, the more information we've gained by knowing X.
This has been an awesome deep dive.
Mm.
I feel like we went from being a little intimidated by entropy to actually understanding how to calculate it and use it to measure information gain.
Yeah, it's pretty cool stuff.
It is pretty cool. And those calculations are just tools to help us grasp the underlying concepts.
Yeah.
The real power comes from understanding how entropy and information gain can be applied in all sorts of fascinating ways.
Yeah, exactly. And that's something we can definitely explore further in a future deep dive.
Absolutely. Well, until next time, keep those minds curious and those calculations accurate. Thanks for joining us.
Thanks, everyone.